Hello everyone. Today we start paragraph 5.6 from PDE book Evans, Sobolev inequality. So our goal in this lecture to discover embedding of various Sobolev space into others. So we want to find estimate of functions in one LP space by another LP space. Like if a function u belongs to v1p, it means u and its derivative belongs to LP, thus automatically this function belongs to another space. Belong to a certain another space. Actually, the answer is yes. And this answer depends from P. Like we should consider three cases when P is equal to greater or equal than 1 less than n, or second case P equal to n, and third case P is greater than n and less or equal than infinity. Okay, in this lecture we will talk about first case when P is greater or equal than 1 and less than n, which calls Gagliardo, Nirenberg, and Sobolev inequality. So what is actually before starting proving and talking about this theorem, let's start with some motivation. Actually, our P is greater or equal than 1 and less than n. We ask whether we can establish an estimate for u LQ in Rn less or equal C du LP Rn for certain C which depends only P and N. C doesn't depend from U. So where our Q should be greater or equal 1 and less than infinity. And for all U, which is compactly supported, and infinity in Rn. Okay? So first let's find out for which Q this inequality is true, because we cannot say this for all Q is this is correct. Therefore, we start with some motivation. We say that if this inequality number 1 is true, then it cannot be for arbitrarily Q. Therefore, we have to find such Q, specific form. So for this we choose U which is compactly supported in infinity in Rn. So also you should be not equal to 0, because like automatically it become incorrect, because or u also cannot be constant, because derivative of constant is 0 and u is less than 0. This is incorrect. So let's first we define the scale function. What's the scale function? We have u lambda of x, which is equal to u lambda x. This is the scale function. Like this is correct for all lambda. Now we apply to the inequality this scale function u lambda L Q R N is less or equal to say norm of du lambda LP in Rn. Let's write definition of LQ. What does mean norm in LQ? U lambda LQ, it means equal to integral absolute value u lambda power q, but 1 over q dx. So now our integral is equal to u lambda x q like dx per 1 over q. We are integrating in Rn. So when we do change variables like lambda x, we take y. Now our dx becomes like dy divided by lambda power n. Why lambda power n? Because we are in n dimension space. So this will be equal to integral Rn u y q dx. We can take out lambda minus n divided by q, and this one 1 over q. So now we have lambda minus n divided by q norm u in LQ Rn. So let's do for definition lambda du lambda LP Rn. So because like we are taking derivative of u lambda x now, we have to write this one as like d u lambda x. We have to take again derivative of lambda, therefore we need multiply by lambda power q, both of them, this one also 1 over q. Okay, this becomes lambda times integral d u lambda x power q divided in the power 1 over q. Then when we do changing variables again, we get sorry, dx should be here. We get lambda like times integral of duy q times lambda power minus n, but divided by q, because we have here q. Here 1 over q. So this becomes lambda 1 minus n divided by q times d u lp. Sorry, whenever I wrote q, we have to change with p, because now we are considering lp. Here p, not q, p. Everything should be p. Then Rn. So let's put in our inequality number 1. We got like lambda minus n divided by q u lq Rn less or equal than c times lambda 1 minus n divided by p du lp in Rn. So now we take this on the right side. We get u lq less or equals c times lambda 1 plus n divided by q minus n divided by p du lp and Rn. So now our inequality, like in this side and in that side, we don't have lambda. We don't have dependence on lambda. So when 1 plus n divided by q minus n divided by p is not equal to 0, this inequality becomes incorrect, because we have to choose lambda. For example, when we take lambda to 0, it becomes incorrect, because norm of u less than 0. Or we can take lambda, like we can take bigger, and it becomes absolute value of u, like norm of u, less than infinity. So still less or equal than infinity. Still it will be incorrect. Therefore, only case it works when 1 over this inequality is correct, when 1 over n is equal to 1 over p minus 1 over q. Or in other words, 1 over q, 1 over n minus 1 over p is p minus n divided by np. So q should be np divided by p minus np, n minus p should be. Sorry, where I did mistake. Or here 1 over n, 1 over q is 1 over p minus 1 over n. Here should be minus, here also minus, here also minus, which is equal to np divided by n minus p. Okay, now let's call this one p star. This calls like Sobolev conjugate. Definition: if p is greater or equal than 1 and less than n, Sobolev conjugate p star is equal to np divided by n minus p. Also, we know that 1 over p star is equal 1 over p minus 1 over n. So p star is greater than p. strictly. So our scaling method shows us that the inequality of Gagliardo Nirenberg is correct only for q equal to conjugate. Assume p is greater or equal than 1 and less than n. So there exists c, which depends only n and p, such that inequality u lp star in Rn is less or equal c du lp in Rn for all u which is compactly supported and one's derivative. Compactly supported and have a continuous derivative. Okay, this is theorem Gagliardo-Nirenberg inequality. Also, we should mention that this compactly supported is important because, for example, if we take 1, u1 is not compactly supported, but du becomes equal to 0. So this is important. Okay, let's prove. Proof of this theorem we will do in 2 steps. In the first step, we take p is equal to 1. For p equal to 1, since we know u has compact supported for each I 1 to n and x Rn. Also, u is C1. So, using fundamental theorem calculus, we can write ux is equal integral minus infinity until then xi, u derivative with I components, u x1, x2, xi minus 1, but here we should change variable y1, yi, xi plus 1, and xn, byi. Okay, this is just definition of like ux. We can write it like this. Now let's take absolute value ux. We know that this one is less or equal than minus infinity to xi, xi. Okay, I will not write this one. You know what I mean. Here we have absolute value inside. Now this one is less or equal than minus infinity until xi. If this is less or equal the sum of xi uxi square. So I can write this is equal to minus infinity xi du dx, and also this one because both sides is inside absolute value, we can take this x1 greater and greater until the infinity plus infinity du dy. Sorry, everywhere should be dyi. Now what we have? We have u of x is less or equal minus infinity and plus infinity du dy I. This inequality is correct for all I 1 to n. Therefore, let's multiply all of them. It becomes ux for n less or equal than the product e from 1 to n minus infinity to plus infinity du dy e. Okay. Now we take in power 1 over n minus 1 from both sides. Ux n divided by n minus 1 less or equal then product e1 to n minus infinity plus infinity du dy I. We take from both sides this power. Okay. What we do next, we take the integral from both sides with respect to x1. Ux integral from minus infinity and plus infinity integral of e is equal to 1 to n minus infinity to plus infinity integrals minus infinity to plus infinity du dy I 1 over n minus 1. So let's write this one in a simple way. This is inequality minus infinity to plus infinity. We have integral minus infinity to plus infinity du dy1 times product e equal to 2 to n integrals minus infinity to plus infinity du dy I. One n minus 1 here also 1 over n minus 1 dx1. See that in this integral we are independent from x1. So this one is constant with respect to x1. Why? Because what does mean ux? This is here we had dependent from xi, but when we made inequality we write like less or equal the dy. Here still we had dependence from xi here, but when we made this one like less or equal to plus infinity, now here we don't have any dependence from I1 x1, sorry. So this is like ux less or equal minus infinity plus infinity du. Here we have I1, x2 and xn dy1. So we don't have I1. So if we don't have dependence from I1, it means this one is constant. We can take out from integral. So this is equal to integral minus infinity plus infinity du dy1 power n minus 1 times integral minus infinity to plus infinity e equal to n minus infinity to plus infinity du dyi 1 over n minus 1 dx1. So what we will do here, now we use generalized Holder inequality. What was Holder inequality? Like if f g are in L1, is this L less or equal than f in LP times g in LQ, when 1 over p plus 1 over q is equal to 1. This simple like Holder inequality, but for generalized one, for example, we have W1, Wn, n minus 1. Let's take n minus function. This is in L1 less or equal W1 LP1 W2 LP2 Wn minus 1 LP minus Pn minus 1. So, and also this sum pi 1 over pi should be equal to 1. Let's write just definition. This is integral of W1 Wn minus 1, okay, absolute value dx is less or equal than integral W1. What is our pi 1 over n minus 1, because the sum of 1 over n minus 1, we take all of pi n minus 1, so this becomes like times integral W2 n minus 2 n minus 1, and all of them Wn minus 1 n minus 1, all of them in the power of 1 over n minus 1. This was generalized Holder inequality. Now let's use for this inequality this generalization. Like we have integral of product a lot of function n minus 1 function, which all of them are in the power of 1 du dy2, like n minus 1, here also minus infinity plus infinity du dy and power of minus 1. So this is our W1, W2, Wn. So when we take W1 power n minus 1, this becomes just this integral, okay? So this product of these integrals with respect to this integral, it becomes like integral of this function less or equal integral minus infinity to plus infinity, integral minus infinity to plus infinity du dy true, but all of them should be okay in power 1 over n minus 1. This one become 1 because we had 1 over n minus 1, and with this power n minus 1 it becomes 1. So times minus infinity plus infinity du dy is 3, and so on du dyn. So we got eventually that integral of ux power n divided n minus 1 minus infinity to plus infinity dx1 is less or equal than integral of minus infinity to plus infinity du dy1 times product of e equal to 2 until n minus n, product of doubles integrals du dyi I2 into the, and all of them in power of 1 over n minus 1. So what we should do next, like we have to take integral again with respect to x2 ux n divided n minus 1 dx1 times dx2. This will be less or equal than minus infinity to plus infinity minus infinity to plus infinity du dy1 times like product e2 to n du dyi power 1 over n minus 1. This is here. Now times dx2. We are taking integral with respect to x2. So let's see again, we have here one integral which does not depend from x2. Why? Because in the we had du integral du x1 y2 dy2 here, second integral here, first integral here from n when I is equal to which is not depend from x2. So we should take out this one out of integral. Du dy2 power 1 over n minus 1 times, now minus infinity to plus infinity, we have minus infinity to plus infinity du can't, I forgot here 1 over n minus 1. Yes, here also. Now here we have dy1 1 over n minus 1, and we have again the product of from I equal to 3 until the end, because we take out when I is equal to 2 minus infinity dx2. So here we have n minus 2 terms, because n minus 3 plus 3 plus 1, n minus 2 with this one becomes n minus 3 term. We have product of n minus 1 integrals. Again, we have to use generalized Holder inequality with same idea, because we have here first integral like power 1 over n minus 1. This is w1. Okay, and this n minus 2 product will w2, w3, wn. So we can conclude this is less or equal du dy 2 1 over n minus 1, but here now we write product of this one. This becomes integral minus infinity plus infinity minus infinity plus infinity for the first one, du dy 1 here we don't have power, because like w1 this is less or equal w1 power n minus 1. N minus 1 will cancel with this n minus 1, and at the end we have 1 over n minus 1, but the product will change with integral. E is equal to 3 to n. This we have 3 integral. Du dyi 1 over n minus 1 dx2. Okay, now we will continue doing like this. What you will get at the end, like this one always like decreasing, but here it will be increase, but always we can use generalized Holder inequality, because we always have n minus 1 product which are all with same p, I mean with all same power, but always one of them we take out. For example, from now for taking integral with respect to x3, here we have one triple integral, we should write here, okay, and we have this one, it will be triple integral, this one also triple, and here will be for integral for components. Like immediately I can write this third case, ux then divided by n minus 1 x2 dx3, it will be like this. First we take out three integrals du d dy 3 dy 3 sorry, I forgot here writing dx1. We have dx1. First we took the integral from with respect to x1, and then we have dx2, but we have dy3. Here also I need to write dx2. Now at the end we have x1, x2, and ye. So this one less or equal to z1, and times next this will be times triple integrals of du dx1 dy2 dx3. Okay, and times this one triple integral du dy1 dx1 and dx3. Okay, but here will be product of a equal to 4 to n this 4 integrals. So when we do this n times, we get integral Rn u x n divided by n minus 1 dx. Okay, less or equal here n time integral, but we have du dx1 dx2 dx3 and so on. And then we have the dyn dxn. Always this will be increased by 1. We take n minus 1 times this is n minus time, but last one n time. When we do last time, it becomes like all of them product of e equal to 1 to n for these integrals. So this is our du dx power n divided by n minus 1. So what we have done now, we did that dx norm of u with respect to n ln n minus 1 is less or equal than c times our c here is 1 as du dx because our p is 1, here should be power 1, so I take okay. Now we should take out this one because we have this means this one square and square root of this one. Okay, now we proved for p is equal to 1. We proved, and our c is 1. So how to prove for all p? Step 2, we say that for p less than n greater than 1, we write again this inequality, absolute value u, n divided by n minus 1 dx is less or equal for du dx for n divided by n minus 1 for all u. Let's take like u equal to v, okay, and okay, v power lambda, you can take v power lambda, so now v power lambda times n divided by n minus 1 dx less or equal than d v point lambda dx power n divided n minus 1. So from here our v lambda n divided n minus 1 power of n minus 1 divided by n dx less or equal, or ds should be inside, less or equal, then here we should take derivative of this one. It will be alpha dv times v lambda minus 1 dv dx. So this is equal to lambda times absolute value of v lambda minus 1 times dv dx. Now we use here Holder inequality again. We can write this is less or equal alpha, then u v power lambda minus 1 times 1 minus 1 over p, okay, and square root of this one, p divided by p minus 1 times du over p 1 over p. Now we need to choose lambda such way. Here is lambda. V lambda minus 1 times p minus 1 divided by p minus 1 times integral du p 1 over p. We need to choose lambda such way that this one like becomes similar to this one. In order we could like take this one to left side. So here most suitable lambda should be lambda minus 1 times p minus 1 divided by p. Okay. Divided by p. Oh, sorry. Here should be p minus 1 divided by p, but here should be p divided by p minus 1. Because the sum of these two should be equal to 1. Here p divided by p minus 1. So so this one is equal to lambda n divided by n minus 1. Why? Because now inside of integrals both are same, and I can take this power to the side. So it will be now solid value v divided power lambda n divided n minus 1 dx n minus 1 minus n minus 1 plus 1 over p less or equal then lambda integral du for v 1 over p. So this will be v lambda n minus 1 dx 1 minus 1, okay. Here power 1 over p minus 1 over n should be pn n minus p, like this. Lambda integral du 1 over p. So when we take lambda n minus 1 equal to np n minus p, lambda becomes p n minus 1 divided by n minus 1, which is greater than 1. So here n minus p. So this is our p star. Like our p star is np divided by n minus p. So now we have proved that integral Rn u power p star dx 1 over p star less or equals C Rn du P dx 1 over P. Okay. Thank you for listening. If you have any question, you can comment. Hopefully you enjoyed it.